No.
Yeah,
Let's
that's
start it
start.
now.
Awesome.
Yeah.
Okay,
Okay.
yeah. Sorry, continue.
Yeah.
Start from the yeah.
Okay. So today, me and Sahiti are going to be talking about PCA, SVD, and various other dimensionality reduction techniques. But the first thought that should come to your mind is that why do we need to reduce dimensions at all? Why are we doing this exercise? If you think from a very naive point of view, you would think that if you have more dimensions, you would have more features about the data, which means you would have more information about the data, which means your model should perform better, right? Well, this is not the case all the time. So there are some reasons that we need to reduce dimensions for. So the first reason is kind of simple and intuitive that we humans are three-dimensional beings, and sometimes when we need to infer data, we need to reduce the n-dimensional vector space that we're working with to some human comprehensible 2 or 3 dimensions. And on top of that, there is a mathematical phenomenon called the curse of dimensionality, which I'll explain. As you can see, this which is casting this bad spell on ChatGPT. But yeah, okay. So what's the curse of dimensionality? So as the number of dimensions in your data increases, the data starts to become sparse, as in the distances start to become the same because there are so many dimensions. When you get the distance for every point, it tends to be the same for every point. So in high dimensions, all points will tend to appear equally far apart. And one more thing is that if you increase the number of dimensions, the complexity of your models will increase because the neurons will increase. And that increases the risk of overfitting and the higher chance of fitting noise. And if you have to maintain density and clustering in the data, you will have to have more data, and the data requirements will start to grow exponentially as you increase the number of dimensions. So there are a lot of dimensionality reduction techniques that we can apply, like PCA, TSNE, autoencoders, SVD, and these techniques help us by projecting the data into lower dimensions while preserving local or global structure depending on the technique. So the two methods that we're going to be discussing in detail today are principal component analysis and singular value decomposition. So I'm going to be talking about principal component analysis, while Sahiti is going to be covering SVD. So first of all, what is the difference between features extraction and feature selection? There are two ways that you can reduce dimensions, two ways you can reduce data. So the first is feature extraction. Feature extraction basically transforms the data that you have into another comprehensible way, like it into a new feature space basically. It often reduces dimensions and it creates new features from the combinations of the original features. And this is particularly useful when features are correlated or linearly dependent on each other. So you don't need to have 2 or 3 features when you can only have one feature that represents what those 2 or 3 features are conveying. Feature selection, as the name suggests, it keeps a subset of the original features that you have. It does not do any kind of mathematical transformation. You just filter out the irrelevant or noisy features which encode noise or the data which is not very necessary to you. So you keep the top K features and top K features which preserve the most information about the data, and you remove the rest. And the good point about this method is that it maintains the interpretability that you had in the original features. So what kind of technique is PCA? So PCA is a feature extraction technique. Here we do some math to create meaningful combinations of features. What is meaningful, we'll discuss in a bit. But yeah, it is a feature extraction technique. We will be doing some transformations to the data that we have, and we are going to be reducing dimensions using that. So, okay, let's delve into the math behind PCA now. So first of all, we need some prerequisites. So the first thing is, what is the basis of a vector space? So the basis of a vector space is a set of n vectors such that the span of the set of these vectors is the whole vector space. What this basically means in simple terms is that you can express any vector in that Rn vector space in the linear as a linear combination of these basis vectors. So here is a simple example. Span of I cap and j cap is R square. So any vector in a planar space in R square space can be expressed as a linear combination of I cap and j cap, which is pretty intuitive and we're all familiar with. And you can expand this to any n-dimensional vector space as well. Second is change of basis. So change of basis is when you have a vector in a vector space and you can express it as a linear combination of a different set of vectors than the ones that you had before. So instead of instead of representing a vector as a linear combination of I cap and j cap, I can write it as a combination of I cap plus j cap by root 2, I cap minus j cap by root 2, a different basis vector. So you do this operation by a transformation matrix. So this is, say, your vector A, and this is your vector B, vector in basis B, vector in basis A. And this is X, a transformation matrix, which kind of linearly transforms it from one to the other. And this is an example, as you can see. A is just I cap and j cap, and B is some arbitrary vectors that we have chosen for our basis vectors. And if you apply this, you get the vector VB prime in terms of the basis that you've chosen, the new basis. This is a simple mathematical operation. Next, we need to discuss about variance and covariance. This is something from statistics. So a variance of a random variable is defined as this, 1 over n or 1 over n minus 1, anything works. Summation I belonging from 1 to n, xi minus x bar whole square. And x bar is the mean of the data points, mean of xi. And the covariance between two random variables x and y is defined as this, 1 over n minus 1 summation I ranging from 1 to n, xi minus x bar into yi minus y bar. So covariance is a measure of uh, how much a variable changes with respect to other variable. So if the covariance is very high, that means that if you change x a lot, y will also change a lot. So covariance is basically how much two random variables are linked, how much two random variables depend on each other. So that is the intuition behind covariance. Next, we define a covariance matrix. One thing that I have written here is that you have to normalize the data before uh, kind of working with it. So you have to make sure that all the data is mean centered and standard, and you divide it by standard deviation, so that the reason behind this is so that one variable does not dominate over any other variable. So say some factor is, say, age. Age would only range from 0 to 100, right? It won't be a very big number. But some other feature that you have is income. Income might go from anywhere from 10,000 to 1 lakh to 1 crore, who knows? So that feature is numerically greater, and it might end up dominating over the age feature, which might be more relevant to whatever task you're doing. So that is why you try to normalize all the variables. Uh, yeah, 1 second. I'll just stop here to ask if anyone has any doubts in what we've covered before this, before going further.
One doubt.
Yeah,
You said PCA preserves the interpretability of the data. What did you mean by it?
not PCA. What I meant, as I said, selection preserves the interpretability
Okay,
of the original
fine,
features.
fine.
Yeah. Anything else? Okay, fine. We'll go forward then. So this is the covariance matrix CX. This is a square matrix, as you can see. So yeah, first of all, before that, X. What X is? X has the rows as its features, and no, wait, sorry. Yeah, the rows as its feature, and each row has a data point. So m cross n, m number of features and n number of data points. So yeah, this is X, and as I just said, you normalize the data so that one feature does not dominate over another feature. So this is how you define your covariance matrix Cx, 1 over n minus 1 x into x transpose. And as you can see, this will become this matrix. This is a symmetric matrix because the covariance of x comma y is the same as covariance of y comma x, as you can see from this formula. Covariance of x and y is same as covariance of y comma x. So this will become a symmetric matrix with the diagonals as the variance of the same random variable. So yeah, this is the covariance matrix. A couple of points to note about this matrix is that it is a symmetric matrix, as I just said. And the second thing is that the eigenvectors of a symmetric matrix are orthogonal. This is a linear algebra fact that we are going to prove now. And this is very crucial to how PCA works and why it works. So this is the proof of orthogonality. So Cx is an m cross m symmetric matrix, and it has n real eigenvectors and corresponding eigenvalues. So you take any of those two eigenvectors and their corresponding eigenvalues. So Cx_v1 is lambda1v1, Cx_v2 is lambda2v2. So you take the first equation, you forward multiply it with v2 transpose, and you take the second equation and you forward multiply it with v1 transpose. What you get here is this thing, right? And v2 transpose v1 is the same as v1 transpose v2 because this is just the dot product of two vectors. Now, I have not added the exact derivation here yet, but you can see you transpose this line. If you transpose this line, lambda2 is a constant, it will stay out. This will come here, it will become v2 transpose v1, same as this. And it will also become transpose. It will become v2 transpose cx transpose v1. I hope everyone understood what I did, right? We transpose this line on both sides. Okay, I'll take that as a yes if no one has any doubts. So yeah, we transpose it. Now, the property of symmetric matrices is that Cx transpose is the same as Cx, right? As you can see from here that the Cx transpose matrix will be the same as Cx. Now, so you can replace it here, subtract these both sides. So it will become lambda1 minus lambda2 into v2 transpose v1 is equal to 0. Now, lambda1 and lambda2 are any two arbitrary values, and they don't necessarily have to be equal, which means that v2 transpose v1 has to be 0, which means the dot product between these two vectors has to be 0, which means that these two vectors are orthogonal. I hope that's clear. If there are any doubts, please ask.
One small doubt. Why are we taking n minus 1 in denominator instead of n? Like, is it significant?
No, it's not significant. There are sources which use 1 over n as well, and there are sources which use 1 over n minus 1 as well. It doesn't matter because in most cases our data set is going to be huge anyways. It's like
Okay.
10,000 or 9999. Doesn't really matter that much.
Yeah.
Yeah. Anything else? Okay, we'll move forward then. So now we move on to the actual mathematical derivation of PCA. So these are some conditions that we need to specify. So the basic operation of PCA is to linearly transform the data that we have. So y is just p into x, it is just a linear transformation. And there are some conditions that we put on y. So the first one is that the features of y are called principal components, and they're ranked according to the variance. So when you linearly transform this data, you create a new set of features, right? The rows. So the rows with the maximum variance in them are called the principal component, the highest principal component. So the row with the maximum variance would be the first principal component. The row with the second highest variance would be the second principal component, and so on. And the second interesting fact about this matrix is that the covariance of y must be a diagonal matrix. We want the covariance of y should be a diagonal matrix. Does anyone want to answer why that should be? Why should the covariance of y be a diagonal matrix?
Because like you would want the covariances to be close to 0, like, and you want them to be independent of each other, right?
Yeah, correct. So you want that one feature does not depend on any other feature, so that as I just said, the covariance is a measure of how much a feature depends on the other feature. So if the covariance is a diagonal matrix, that means the only variance that you have is of the same feature, and there is no relationship between any two other variables. So that is why you need the covariance to be diagonal matrix. So yeah, here one assumption is that information is considered to be stored in the variance. The variance of a feature is considered to be proportional to its information content. So the higher the variance, the higher its information it stores, which makes sense. So our goal now is to find the transformation that we're going to do to X to get this transform matrix Y, and then we can extract the features that we want. All right, so this is the derivation. You take the covariance matrix of Y. You write it 1 over n minus 1 y transpose. And one important thing to note here is that because we're just linearly transforming the data, you're not shifting the origin, you're not doing anything. It's just basically rotating and stretching. That's pretty much what you're doing. So y will also be a zero-centered because x was zero-centered. So P is a simple linear transformation. Then you substitute y as Px, and yeah, you go here Px x transpose P transpose. So you get P Cx. As you can see, xx transpose over n minus 1 was the covariance matrix of x that we defined. So the covariance of matrix of y is P Cx P transpose. Now, symmetric matrices are orthogonally diagonalizable. This is one more property of symmetric matrices, which you can just see here, that say R has an orthonormal set of eigenvectors Cx. So Cx was our initial symmetric matrix. We have listed the orthonormal eigenvectors. We've just proved that the eigenvectors of a symmetric matrix are orthogonal. So we take the unit vectors, we arrange them in a matrix. The columns represent uh, the eigenvectors of Cx. So naturally, RR transport would give you identity because the vectors are orthonormal. So V1 transpose V2 will be 0, the dot product will be 0, and V1 into V1 transpose, the dot product with itself will be 1. So all the diagonals will become 1, and all the other elements will become 0. So RR transpose would give you identity matrix. So then you write Cx R into R capital lambda. Capital lambda is nothing but a matrix with diagonal elements as its eigenvalues. So you can think of it as R, you can think of it as this thing. So you can think of it as Cx V1 is equal to lambda 1 V1, Cx V2 is equal to lambda 2 V2, Cx V3 is equal to lambda 3 V3. It is basically a set of equations written in matrix form for these. And yeah, you post multiply with R transpose both sides because RR transpose is 0. RR transpose is 1. This becomes identity, and this becomes R transpose CXR is capital lambda. Is everything clear till here? Are there any doubts? Okay, I guess there are no doubts then. I hope it's clear what I've done here. And as you can probably see here that equation 3 and equation 4 are of similar form. So you have the Cx here and you have Cx here as well. You compare equation 3 and 4. You can see that P is nothing but R transpose, which is nothing but the transpose of the set of orthonormal eigenvectors of the covariance matrix of the original data. So the original data that we had, X, you take the eigenvectors in a matrix, you transpose it, you get the transformation matrix that you needed for PCA. It's that simple. So also, as we discussed before, because this capital lambda is a matrix with diagonal elements as its eigenvalues, Cy is also a matrix with its diagonal elements as its eigenvalues. Also, the covariance matrix of the transform data is a diagonal matrix, which means that the new features are linearly independent. As Smithali answered, that the new principal components will not depend on each other. And that is what we wanted initially also, that the features that we have should not depend on each other so that we can have maximum information. It's redundant to have 3 features which have the same linear or nonlinear relationship. So now we have identified features which are linearly independent of each other. So we have found P such that the conditions that we specified initially are satisfied now. So, but we still have not reduced any dimensions. We have done a linear transformation. We have found independent components and features, but we still have not reduced any dimensions. It is still an M cross N matrix. So how do we reduce dimensions? So since we considered that information is directly proportional to the variance, and since the eigenvalues of the covariance matrix of the original data are proportional to the variance of the new features of the transform data, which basically means that, as you can see here, this capital lambda is proportional to Cy, right? So the eigen values of the original data, Cx, is directly proportional to the eigenvalues of features of Cy. I hope that makes sense. Is that clear? Are there any doubts regarding that? Did everyone get this? I hope everyone understood this line. If there are any doubts, please pause me. So yeah. Okay, so now you rank the elements of capital lambda, that is the eigenvalues of the covariance matrix of the original data that you had, in descending order, which means the highest eigenvalue will correspond to the highest variance, and you find the features which store the maximum information. So you say you choose the top k features which have the maximum 95% information, and you discard all the other features. So now you have reduced dimensions while storing the maximum information that you want. You don't need more than 95% information. So yeah, you discard the other features. So now you have reduced dimensions from M to K. And yeah, that's pretty much it. That's how you do PCA. This is like the geometrical interpretation of PCA. As you can see, there's one variable, second variable. Data is spread out like this. These are the principal components that you'll get if you run the algorithm. This is pretty obvious. This is the linear regression line. This has the maximum information stored in it. And the second principal component would be orthogonal to the first one. Yeah, that's it in the algorithm. If there are any doubts in the theory or the math or anything in general, please ask.
So the scaling by the variance is essential for the previous step.
See, the scaling by the variance, I was looking at a couple of sources on the internet. It is not always essential. It is mostly essential when the data is the features are kind of skewed. Like one feature is very, very numerically big than the other feature. Then you need to scale, because then you would expect one feature to have a really high variance because its just value is high. Yeah. But if there is not a lot of numerical difference, you can skip that step. That sometimes give better results even. But mean centering is important. You need to mean center the data. Okay. Anything else? Okay, if there's nothing, I guess we can move to the code implementation of this. 1 second, I'll share VS Code. Can you see? Is my screen visible?
Yeah.
Okay, so yeah, this is the code implementation of PCA. First, you import the necessary libraries, and also we use the iris dataset for this. We use sepal length, sepal width, petal width to classify the 3 different kind of flowers. Yeah, everyone knows about this. And yeah, Seaborn, Escalon, these are the ones where you can import PCA directly. But first, we're gonna do it manually. So yeah, this is the data set that we have. So we have 4 features, and you have target. It has 0, 1, 2, 3 different kind of flowers. So the first thing that you need to do is you need to normalize the data. So mean value should be x dot mean. And after normalizing the data, this is just a sanity check to see if the means are actually 0. So these are practically 0. 10 to the power minus 15, 16, this is 0. Then you calculate the covariance matrix. Yeah. Oh, sure. I don't know who asked it, but yeah, I haven't scaled using the standard deviation here because I tried it and not scaling was giving me better results because these values are not that numerically dominant and stuff. So you don't need to scale always. Yeah. So yeah, we compute the covariance matrix x transpose x upon n minus 1. This is different from what I just showed you guys. We're doing x transpose x here because here the columns are the data points and the rows are the features. What we just did there, we had rows as the features and no, we had rows as the data points and columns as the features. So that is a minor change here. So yeah, x transpose x, you get the covariance matrix. As you can see, this is a symmetric matrix. 4 cross 4. Yeah, you also have a direct function to get the covariance matrix x dot cov, and you plot a heat map for this. This is also proves that yeah, this is a symmetric matrix, and this kind of shows which features are kind of correlated to each other in a way. So as you can see, this is basically 0. Its petal length is not correlated to sepal width, but say this one is the ones near white are kind of correlated to each other. Petal length is kind of correlated to sepal length. So you can see how features are correlated to each other here. And then we perform the eigen decomposition using np.lineal.eigen direct formula, direct syntax for it. You get the eigenvalues, you get the eigenvectors. So as you can see, the first eigenvalue has the most amount of information stored in it, second 0.24, 0.07, and 0.23. So you can rank these eigenvectors like that. It's 0, 1, 2, 3. And this is a code to index slicing for descending order of eigenvalues. You just rank the eigenvectors in like the descending order of their eigenvalues. Oh yeah, this is a code for calculation of information percentage, which I just showed you. So you have a moving sum. If you increase the amount of principal components you have, the information percentage will obviously increase. So here you can see that we have plotted this moving average along with the number of principal components, and this is the cumulative variance. This is basically the amount of information percentage that you have. So as you can see, if you take first principal component, you land up around 90%. You take the second one, you go higher, 95. Third one, you're practically there. Fourth, obviously, you can reconstruct. If you have 4 vectors, you can reconstruct anything. But yeah, at like 2 components, you don't need more than 2. You can basically get all the information that you need from 2 components. Yeah, that's what we show here. We take the first 2 principal components. Transform data is x at x dot p. Here also, because our data is transformed, because our columns are the features and columns are the features and rows are the data points. We post multiply instead of pre multiplying this matrix. It's just flipped. It doesn't matter that much. So you have the transform data and you plot the covariance matrix of the transform data here. As you can see, these two are 0. So that means that these 2 features are not correlated to each other. This feature has the highest variance, so that is why it's very red. The variance level is very high. This is lower, but yeah, okay. After this, same thing, PCA and PC1 and PC2. We use the built-in function. There is a built-in function that you can use imported from sklearn. And this is interesting. Here, we take the first principal component, we take the second principal component, and we plot the data points along with their labels. So this is flower number 1, this is flower number 2, this is flower number 3. So you can see that even if we only have the first and second principal components, we can easily draw boundaries here and classify which data point lies in which flower category. We don't really need 4 dimensions. We can only do it with 2 dimensions. So that is how PCA reduces dimensions while preserving data. This is a classic example of that. And yeah, that's it. If there are any doubts in code implementation or PCA in general, please go forward and ask. I am assuming there are no doubts. Fine then, I guess. Sarith, you can start.
Okay, I'll just present my screen. Okay, so we're going to start with eigenvalue decomposition now. Okay, so when you're doing eigenvalue decomposition, it has to be a square and symmetric matrix. Like eigenvalue decomposition is only applicable if you were doing it for a square symmetric matrix. So what is eigenvalue decomposition in the first place? So basically, when you have a vector x and you're pre-multiplying it with the matrix A, and the resultant is just a scaled version of this vector x, then essentially, basically, if it's ax is equal to lambda x, then x is the eigenvector and lambda is your eigenvalue of the matrix A. And the symmetric matrix A can be represented in the form of matrix product between an orthogonal matrix Q, a diagonal matrix lambda, and the transpose of the matrix Q. Here, the eigenvectors are the column vectors in Q, and the eigenvalues are the lambda i's in the diagonal matrix. Again, But that's only applicable if A is a symmetric square matrix. So what do we do if we need to do this? We need to decompose the matrix and it's not a symmetric and square matrix. Like let's say we have a rectangular matrix that we have to decompose. So for all those kind of matrices, we use single value decomposition. In single value decomposition, we can write A is equal to U lambda into V transpose, U sigma into V transpose, where U and V are orthogonal matrices and sigma is a diagonal matrix. And the diagonal elements of sigma are basically the singular values of the matrix A. And the column vectors of U are the left singular values of A. And the column vectors of V are the right singular values of A. So now how do we get this sort of derivation? So for matrix A, we know A transpose and A transpose A are both symmetric matrices. So we can find the eigenvalue decomposition of these matrices. So then we can say A transpose A into Vi is equal to sigma I square Vi. And so over here, that means Vi represents corresponds to the eigenvector, and sigma I squared corresponds to the eigenvalue of A transpose. And now if we let some vector Ui, for example, equal AVI by sigma I, then and we multiply that with A transpose, then we get something like A transpose into AVI by sigma I, which we can decompose and finally equate it to sigma I squared into Ui. So that means from here we can see that Ui is the eigenvector of AA transpose and sigma I squared corresponds to the eigenvalues of AA transpose. So by again rearranging that Ui equation, we get AVI is equal to sigma Ui. So now if we let Vi be the ith column of V and Ui be the ith column of the matrix U, then we obtain something that looks like A, which is of the size m into n, into V, which is of the size n into n, is equal to U into sigma. So now we know V is orthogonal. So if we multiply both sides by VV transpose, we get A is equal to U sigma V transpose. So over here, UI, yeah. Okay, so now if A is a M into N matrix, where M is greater than N, A transpose A will have M eigenvalues and A transpose A will have N eigenvalues. So the first N eigenvalues of both would be the same, and the extra M minus N eigenvalues of A transpose would just equal to 0. And additionally, so the eigenvalues would decrease from the first to the nth eigenvalue. So in SVD, when you're finding the SVD decomposition, one thing to note is that the singular values in all of the in the diagonal elements, they are sorted in like a decreasing order. So the first singular value would be the highest singular value and slowly goes on. So the last value in the square matrix, the diagonal square matrix, would be of the least singular value. So now let's do this with an example. So let's say we want to find the singular value decomposition of matrix A. So the first step would be to find AA transpose. So once we find AA transpose, we get a matrix of a 2 into 2 matrix whose elements are 17, 8, 8, and 17. And now we first find the eigenvalues of AA transpose. Now how do we find eigenvalues? We just we find the det of that matrix minus lambda I is equal to 0. And whatever lambda I we get from here would be the eigenvalue of AA transpose. And using this eigenvalue, we can find what the eigenvectors are. So using this, we get the eigenvalues to be 25 and 9. So then coming to the next step. So let's say the first eigenvalue is 25. So now we have to find the eigenvector corresponding to this. So we can just find the vector of the null space of AA transpose minus 25i. So whatever vector that satisfies the null space of that would be the eigenvector because it has to equal to 0. So the vector that satisfies would be v1, which is 1 by root 2, 1 by root 2, comma 0. And similarly, we follow the same steps for lambda is equal to 9. And we get another eigenvector. So now we need to come to the third eigenvector. So the third eigenvector would just be the one that's perpendicular to the first two. So you just solve the linear equations. V1 transpose V3 is equal to 0. And V2 transpose V3 is equal to 0. And that gives you V3 is equal to 2 by 3, negative 2 by 3, comma 1, negative 1 by 3. So now these are basically the right singular values of A. So now we have to compute what the left singular values of A are, which is basically the elements of the matrix U. So we can use the formula Ui is equal to 1 by sigma I into AVI. With that, you get U is equal to 1 by root 2, 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 and negative 1 by root 2. So now we can just use this to find the final SVD equation, where we have the initial 3 vectors from V. You have sigma, which is just the eigenvalues, and the singular values, basically, which are basically the square root of the eigenvalues that we get. And we can find what U is from here. So this is the final SVD decomposition of matrix A. So now let's talk about how we can use this decomposition for dimensionality reduction. Okay, so basically the concept of SVD can be used in tackling the curse of dimensionality. Say we're given a set of data points, like for example, over here, it's this entire circle. And we wish to perform a linear transformation defined by the matrix A. So the thing is, usually when we pre-multiply a vector with the matrix A, we perform a linear transformation, and this helps in like changing the basis of these data points. So if we multiply with this particular matrix, these points transfer to this kind of a format. And okay, so let's talk about it in the form of SVD. So let's write out A as U sigma V transpose. So when you're pre-multiplying A, you're essentially first pre-multiplying V transpose and sigma, then U. So slowly, let's go step by step. So when we pre-multiply with V transpose, we get this kind of format. And then from here with sigma, when you just pre-multiply with sigma, it gets elongated in one direction, and when they multiply with U, it changes its basis and shifts along the axis. So, but in sigma, let's say we neglect sigma 2, which is basically over here 0.44. Let's say we're replacing it with 0. What do you think would happen? Okay, so basically, when 0.44 is approximated to 0, we lose a dimension in the final case. So as in, the data points can be represented, initially data points are represented in the 2-dimensional frame. So by the end, if you replace this value over here with 0, you just cut down the number of dimensions from 2 to 1. And finally, we end up with all the data points in 1 dimension. So over here, an entire dimension has just been eliminated by a single change. This can be extended to remove more dimensions, also in similar fashion. So let's talk about how we can use this for matrix approximation. So, okay, so another form of SVD is, since we can write A is equal to U sigma V transpose, if you look at it in this format, where each of these are individual vectors and these are also individual vectors, we can see that every element can be written as, A can be written as a sum of U1 sigma I into V1 transpose. So basically, what's being said over here is any matrix A can be written as the sum of any, like we say, R rank 1 matrices, where R is the number of diagonal, like say, non-zero diagonal elements in the singular vector, singular matrix. So okay, so why would we care about this? So the thing is, one major consider we talked about was computational space complexity, right, when it comes to dimensions. So while considering large matrices, we don't actually have to store the entire matrix. We might just need to store a much smaller number of values needed to define the rank 1 matrices. So this would give us a low rank representation of the matrix. So if, for example, let's take this case. Over here, A is a 4 into 4 matrix. So over here, this is the sum of 1 rank 1 matrix. This is a sum of 2, sum of 3, and sum of 4 rank 1 matrices. As you can see over here, this and this barely have any difference. In fact, sum of 3 rank 1 matrices, it sums up to a pretty highly precise representation and basically a good approximation of the original matrix. So over here, in this kind of cases, just to transfer the information, we don't actually have to store all of the data. We can just store the data up to like this point. So let's talk about other dimensionality reduction methods. So if you want to keep the most important features, we can use backward elimination, forward selection, and random forest. But if you want to find a combination of new features, you have 2 kinds of methods here. You can either use linear methods or you can use nonlinear methods. In linear methods, you have PCA, you have FA, you have LDA, you have truncated SVD. And in nonlinear methods, you have kernel PCA, you have TSNE, you have MDS, and isomap. So basically, over here, when you're talking about keeping the most important features, what you do is you first use a model, you train it, and then you figure out which features actually cause like the most importance, like which features actually are the most important during classification or whatever, and we take the top K features according to what we need. This is how backward elimination forward selection random forests work. Linear methods we've talked about, and non-linear methods, essentially what we do is we try to find them. Each one works differently. Some of them work in like, for example, let's take kernel PCA. In kernel PCA, what happens is we project the given data onto like a higher dimensional space, and we try to find the linear relations between the data. Okay, with this, I'll done with the theory. I'll just move on to the code. Okay, so in this, first I just took a
1 second.
image from.
Saiti, 1 second. Yeah, if
Yeah.
anyone has any doubts now, you guys can ask right now. Like regarding SVD, like whatever Saiti has covered, if you guys have any doubts, you can ask right now. Yeah, Saiti, I think you can continue with the code implementation.
Okay, so over here I just imported an image from Google, and this is how the image looks when you plot it. This is if all of the data points and everything are stored, like every single point in the matrix, all the information is stored. But let's try decomposing this using SVD. So over here, we're just defining our function, define compress SVD. Or we're using the NumPy library. You have an SVD function in that. This helps decompose the matrix in the form of U, S, and V transpose. And so what we want to do is we want to take the top K elements. Anyways, when we talked about SVD, I mentioned that the diagonal elements are in a decreasing order. So the top ones have the most importance. So we just want to take the top K elements. And so this would be the next compressed thing. So we're just taking the top K elements of all of the matrices. And let's say we're taking K elements to be 1,000, 150, 25, 10, and 5, just to see how this would actually affect the final image. And we're just going to plot it for all of these. As you can see, for these, even though there's 1,000 to 1,000 is like perfect, it's like there's almost no blur, the picture is pretty clear. But even as we come to 50, all of the edges are slightly blurred. Most of the data transferred is still the same. Like we can figure out that this is a dog. Like there's no problem in figuring out what the image is trying to show. And even 25 is fine. As we go along, as we reduce the number, obviously the number of features and the data extracted would be less. But even up until 25, we get a pretty clear idea of what the image is trying to convey. So when we want to store the data for all these image processing methods or whatever techniques, we don't need to store the entire data set, or like matrices and everything. We can just store, like in this case, 25 into 25 parts. So this helps us save on space and helps in dimensionality reduction. Are there any doubts, sir?
Yeah, I have one. So does increasing the K value after a particular point offer like diminishing returns, or like doesn't affect the quality much after a certain point?
I mean, it might, because if you want to keep increasing the K values, that means like the dimensions also increase. So like you have to so you have to store a larger matrix. So like you could have like higher computational complexity and stuff like that.
Right, yeah, okay, makes sense. Thank you.
Okay, that's it. Thank you.
Do others have any doubts? Yeah, if you guys, Saiti, you are done with your content, right?
Yeah.
Yeah, if you guys don't have any doubts, I think you guys can leave. Except Arsh and Saiti, you guys stay back. Other than that, I think people can leave.
Thank you.